Hello everyone, thanks for watching this video. Today I'm going to talk about our work LKA-GCN, which is a large kernel attention graph convolutional network for skeleton-based action recognition. First, let me introduce some background. For skeleton-based action recognition, subjects perform actions and are captured by depth sensors or pose estimation algorithms to generate skeleton actions, then sent into deep neural network to predict action categories. These tasks aim to empower machines to recognize and analyze human behavior accurately, has many indispensable applications such as immersive virtual reality, interactive robot, and so on. In fact, there are different action representations such as RGB video, depth image, and 3D voxel. Why we select skeleton data? Because it has lower computational costs and high robustness for camera view changes and background noise. Recent work modeled human skeleton topology as spatial-temporal graph representation, then sent it into GCNs to learn motion correlation. On this basis, we talk about our work. The first motivation is that how to more accurately model long-range dependencies between joints to generate skeleton graph embeddings with polynomial higher-order approximations. The class of actions depends on the dependencies between joints, which can be divided into direct dependencies and indirect dependencies. Taking the action of clapping as an example, the direct dependency is the natural connection of joints, such as the right hand and wrist. There are still crucial long-range indirect dependencies between the left hand and the right hand. In original GCN, the k-order polynomial of the adjacency matrix A is closely related to the receptive field of feature aggregation, although it seems that the order k can be tuned to capture long-range dependencies. The aggregated window always slides toward the nearest rather than the most informative neighbor. The trajectory is fragile to be trapped in a local loop, namely oversmoothing. As a result, stacked graph convolution operators are unable to model long-range dependencies robustly. Guided by one idea, building up large receptive fields to model long-range dependencies, large-kernel convolution is a simple solution, but is ignored because of the high computational cost. Inspired by VAN, we introduced a skeleton large-kernel attention for this task. The original convolution is reconstructed by a depthwise convolution, a depthwise dilated convolution, and a pointwise convolution. The formula is as follows. Then we integrated the SLKA into the Spatial Feature Extraction Module, SSLKA. SLKA is used to aggregate long-range joint features. We integrate the SLKA into the Temporal Feature Extraction Module, TSLKA, which can extract long-distance temporal features. Convolution is integrated to maintain local receptive fields and extract neighborhood features. We further design a spatial-temporal SLKA module which consists of a branch with half channels ordered by the SSLKA module and the TCN layers, and another branch with half channels ordered by the GCN layers and the TSLKA module, which are concatenated in channel dimension. The ST-SLKA gives consideration to local feature aggregation and long-range features modeling, also improves the channel adaptability of the network. Another motivation is that how to make semantic-related poses to be further focused. We believe that the frames with large joint movements tend to contain more semantic information. Therefore, we propose a joint movements modeling to focus on informative temporal features. First, group the frame sequence. Then compute the benchmark frame within the group by exponential weighted moving average algorithm, EWMA. However, the moving average may be less than the ground truth during the early iterations, so it requires bias correction. The measurement of large joint movements is modeled as a quantitative indicator. Finally, the similarity between benchmark frame and each frame is used to enhance temporal features. Based on two-stream AGCN, we construct a large kernel attention graph convolution network by integrating the above modules. Our contributions are as follow. In the experiments, the effectiveness of our method has been verified on 3 public datasets. We first performed some ablation studies on ST-SLKA. The recognition accuracy with ST-SLKA is 2.7% under cross-sub and 1.2% under cross-view, higher than that of the baseline 2-stream AGCN. And concatenated architecture is more powerful than series architecture. Then we compared the performance and parameters with different decoupled large kernel size. 21 decoupled kernel size is the optimal configuration. To further explore the efficiency of SLKA, we compared the parameters of SLKA, graph convolution, and temporal convolution under different channels, and the parameters with different decoupled kernel size. We can find that SLKA is the lightweight operator and only introduces negligible parameters while expanding the receptive field. Then we compare the performance of JMM strategy with different grouping length. The recognition performance is 0.4% higher than baseline when delta is 15, and JMM is also compatible with some other recognition methods. We visually validated the JMM and the temporal weights corresponding to a group of frames calculated by JMM are visualized with a heat map. This demo shows the hugging. As the action progresses, the weight gradually and reasonably increases, which is consistent with the action semantics. Moreover, we also performed visual validation of the adjacency matrix. The left figure is the original adjacency matrix, and the right figure is the adjacency matrix output by the LKA-GCN, which reflects how strong the dependence between joints is. The darker the color, the stronger the dependence. For the action of walk apart, we can find that the dependencies of some joints such as left ankle, left foot, and right foot are significantly stronger. In addition, recognition performance was also compared with some state-of-the-art methods on NTU RGBD60, NTU RGBD120, and Kinetics Skeleton 400. Our method achieved competitive performance and outperformed baseline significantly. Finally, we also try to generalize our method to other data modalities and lightweight the recognition model via knowledge distillation, and our further work is under review.